Hi, good morning, all.
Good morning, everyone.
Good morning.
Good morning.
Good morning, everyone. We have how many? Okay, 30. Maybe we'll wait for 2 more minutes and then get started.
Good morning, Dr. Anupama.
Good morning.
Dr. Anupama, did you get a chance to get connected to the course portal?
Yes, I will give all the updates. Just let's wait for maybe 2 more minutes,
Yeah.
and
I
once we have
just
enough
checking.
quorum, we'll just get started.
No problem. I just checking to see if you got uh,
Yes.
access.
My login got fixed early last week itself, and I could get into the portal, validate everything for myself.
Okay, thank you.
It's the same link. Okay. Okay. So we just had 4 more people joining. Maybe people will join later. We will get started. Okay, so I first wanted to address a common question that has been coming multiple times. So, what is interference? Okay, what did you guys understand about interference? Maybe any one of you who would like to speak, unmute, and what do you understand? What is interference?
Um, Interference is like a positive interference or is the or the way colliding with each other and how it is going to impact.
Um,
It can be adding to each other or it can be
Sorry, you
destructing.
were not, Sorry, I couldn't get you very well. Could you please repeat?
Yeah, interference is like how the waves direction on different amplitude and how it can add up to each other or might be contradicting or negating to each other, and that is what at high level I can think of.
Okay. QC74.
Yeah, at least, I mean, interference, we have different connotations in different sense. I mean, what the previous person was telling, I think that is more to do with, the two waves, Young's double slit and things like that. But I think what we are, at least with respect to the quantum computing, if you ask what is interference, it is due to, presence of some strange signals, like EM signals, which could, disrupt the qubits, or there could be some variations in temperature, and because of that you could have some errors creeping in due to these kind of factors. So at least that's what I would think about interference in the quantum computing sense.
Okay. Anyone else wants to take a QC14? Yes, please.
As QC74 said, I related it to decoherence.
Was it mentioned or taught by Prabha in the first module somewhere?
No, this was not addressed, Dr.
Okay,
Anupama.
okay. So maybe let me take a stab at it. Okay. So you guys know that in quantum we have certain types of things which distinguish quantum from classical. And what are they? First is a very large Hilbert access to a very large Hilbert space, right? Unlike in classical, we have say 0 and 1 are two states. Here we have 0, comma 1, comma all possible linear combinations of 0 and 1, making it a very, very large state that I can access. And if given that is true, if one single qubit has the potential to do a lot of computation. Now, how can they do this? Because they can be put in something called superposition state. So all these linear combinations, the states that I'm mentioning, they are actually some superposition states of this qubit, right? Now, along with superposition is a very powerful. I mean, the first, let's say when we talk about, okay, I'll give this bad analogy. I don't know good or bad. So let's say Ma Durga has 10 hands, right? And she has 10 weapons. So one of the weapons that quantum has, assuming quantum is Ma Durga, is superposition. Now, the second weapon is entanglement. And I think superposition and entanglement have been pretty clear to all of you, right? Superposition gives you this large state space. Entanglement gives you the ability to, if you can entangle two qubits and then you take them to far poles, like we theoretically say, even if they are poles apart and they don't know, I don't know where the other qubit is. I am one of the qubits, I've been entangled with someone and that other qubit has gone very far. I can still exchange information, or I can still do things. And if you can just have the ability to measure me, you exactly know what that other qubit is doing, even without knowing where that other qubit is, right? So entanglement again is a very powerful thing, and we use entanglement as a resource to do a lot of things in quantum, right? Now, similarly, there are several other things, right? Like interference, like tunneling. Now, as the name indicates, and QC74 or 14, you guys thought that interference means like something objecting to and so on. In quantum, however, it is not exactly, I don't know, okay, why they are named in this way. But yes, maybe the naming is not correct, or the naming means differently here in quantum, right? So interference, as QC89 was mentioning, you can think of interference is one of the phenomena that enables us to amplify something and diminish something. Now we can use it in a way, for example in Grover's we use it in a way that we amplify the correct answer and diminish all the incorrect answers, right? So that is basically what we mean by interference, right? Although verbatim it means that something interfering, and so you guys would have thought that okay, interference might mean something interfering with the qubit and decohering the qubit. Yeah, I mean, linguistically it's correct. Unfortunately, in quantum, this is what they mean, that the ability to change the probabilities of these qubits, right? In certain way, right? And that you can control how you want to, like how you want to entangle the qubit is in your control. How you want to ensure or activate interference is under your control, and so on, right? There is one more concept, which is tunneling. So I don't know if I have mentioned this before, but a very layman example way I will try to explain. So you have a wall and you have a ball in hand, right? And you hit this wall with the ball you have in hand, and the ball bounces back to you. You catch it. You hit it again. The ball bounces back. You catch it, right? Now this is something that all of us can visualize very nicely. Now think this ball is an electron, and this wall is basically the electronic orbitals of the molecule. So I am a molecule, I have my electron in my hand, and I'm just throwing these electrons to different orbitals or different states. Now the ball doesn't bounce back to me, but the ball crosses this wall and goes ahead without breaking the wall, right? Now while this, I mean, picturing this in the classical world, or in our in the ball analogy is not possible, right? If the ball has to go through the wall must have a crack, right? The ball has to break. But in an electron, you can very well think that, oh, there are so many gaps. The electronic orbital is like this. There are so many gaps. The electron escaped from its orbit. It was so excited that it escaped from its orbit and it went through and it shifted to the next orbit. That is called tunneling. These are effects. These are effects that we can observe in the subatomic world. And if you guys have seen that, when Einstein had said, right, he's called it a spooky behavior, right? Because he was not able to understand how is this intuitively it is not possible. But in the subatomic world, all of these things happen, right? So in quantum, this is another phenomena called tunneling. I will tell you where each of these things help and why am I concentrating on all these four powers, while you would say that, okay, quantum has a lot of other powers. Why am I so fixated about these four? While the first two, you guys, I think, have a very good understanding. The third, I felt that there was a question that quantum in the assignment, where a couple of people have been wrong about it, and even the NPTEL people were very concerned. So they were asking me that, okay, QML is I don't exactly remember the question, but not affected by one option is noise, and one of the options I think is interference time. Now, why is noise the correct answer? Let me explain. So noise is something that happens in the quantum systems, as we all know, right? And because it's a physics phenomena, so it will always be there. It's just that when we talk about fault tolerant quantum computing, there is no noise in the fault tolerant systems. There will be noise in the fault tolerant system, but but our ability to threshold or contain the noise to say something around 10 to the power minus 6, which is the dream, will be that's the dream threshold, right? We want to be able to contain noise to that level, that then we have the ability to correct that level of noise, right? That is what is fault tolerant whenever it comes. But this pre-fault tolerant, we know that our noises are in the order of 10 to the power minus 3 or 10 to the power minus 4. Right? But and we complain about noise in the cases like quantum simulation or quantum optimization. Yes, we know that, okay, because of noise, my results are not getting as close to, say, the chemical accuracy and so on, right? Or because of noise, I'm unable to train, say, or learn a very deep quantum circuit, because after a certain number of gates, I'm crossing the decoherence time of that particular qubit. However, think of this, and noise, and there could be a lot of places where noise can become your friend, not just in quantum machine learning, right? So if I am able to characterize this noise and use this noise to add generality in my data, I can use it. You will hear a lot of people in cryptography saying that, okay, there are so many ways. And in fact, yesterday I was at an event, and Professor Gautam Pal was constantly mentioning this, that noise is always not bad, right? It's just that we don't know very well to use it, and that's there are a lot of fields that are not able to appreciate. Quantum machine learning knows that, okay, we can use noise to create better generalization, right? We can use noise to prevent overfitting in quantum, right? We can use noise to generate better state spaces. Or in cryptography, we can use, if we can model and characterize noise, we can use noise for, say, things like randomized benchmarking, right? Or creating random circuits, right? So there are a lot of places where actually noise helps, and quantum machine learning is one such area where the other factors, if you look at the other options, all the options actually affect it or dampen it, right? You can argue that, okay, after a certain level, maybe the noise will also be a problem, and that is the reason why we are unable to, say, train very deep quantum circuits. But that is across everyone, right? But theoretically, one thing that we can say is, in comparison to other fields like, say, quantum simulation or quantum optimization, quantum machine learning is relatively a field that treats noise as a friend and not gets severely dampened. So if you do these experiments, so if you run, say, a quantum ML algorithm on your simulator, say, I mean, whatever it is, a small circuit is fine, and then you run that same small circuit on a hardware, you'll see that the numbers or the results are not drastically bad, right? If you had got something like a 60% accuracy, let's say, you might get, say, a 54%, 55%, or 56%. You'll not suddenly start seeing that, okay, my 60 became 20, 30, right? Versus if you do a similar experiment, similar sized circuits, of course the algorithms will be different, but you do a similar thing for, say, molecular ground state estimation, or QAOA for quantum optimization algorithm, you'll see that for several cases, for example, in the optimization, you are probably way ahead and stuck in some other local minima and not being able to go to the global minima, right? Because of noise. Or for quantum simulation, a major problem becomes due to that noise. I mean, if it's a variation algorithm, it's even more dangerous. It is very difficult. But let's say it's a non-variational algorithm, you are finding that the bit strings are so jumbled that it is very difficult to then distill out the correct bit string, right? Because you have got, say, several bit strings with very high count. Now, typically, I mean, just a layman thing, I would assume that my correct answer should have the highest I mean, that the correct bit string should come maximum number of times. Let's say I have run it for 10,000 shots. I would say that, okay, 9,000 times my correct bit string should have been sampled, and 1,000 times there would be other noises. However, that is not the case, right? You would see that, I mean, distilling bit strings is a very difficult problem. So noise relatively affects these areas significantly bad. However, for, say, cryptography, for quantum machine learning, people are able to characterize this noise, trying to understand this noise, and trying to use this noise for the benefit. So that's the reason that answers option B, noise, is correct. Does that help now?
Yep, Dr. Anupama, this is Bhaskar.
Yeah.
I was the one who raised this one.
No, not just you, not just you. You had sent an email that Kohila had showed me, but there were other people also who had some other options. No, so not everyone said interference is different options. So I thought that was not clarified. Yeah.
Yeah, exactly. But what I want to say is, it was not just interference. They gave the option as interference time. That is why it was confusing. I mean, I brought this one up last week in the live session also, and it was not just interference would have made sense. Like you said, means we know what is interference in quantum computing. Like you have explained, amplifying the results or nullifying the results. Those are the things we know. But what interference time? It is written as interference time is the option. That is why it did not make sense. It was an irrelevant one. Of course, if you look at less number of qubits, it's not really a limitation or a concern, because we know that NISQ always has a limited number of qubits, and with QML we can run circuit, we can run the everything with limited number of QML.
Just to clarify, that NISQ has no connection with number of qubits. It is not like
Exactly.
Niskera will have less number of qubits. No, no, just hold on. So when Preskill said this is a Niskera, what he meant is noisy intermediate scale. So intermediate scale, he did not have a proper definition. He's an academician. He did not have a proper definition that how far industry will be able to pack total number of qubits. That's why he says intermediate scale, right? Now he says noisy because we know that today the sort of quantum computers, see, quantum error correction, we knew that quantum error correction has to be established 30 years from now, right? That time you will see there is a lot of quantum error correction algorithms have been already established. We have still not been able to have a proper implementation of quantum error correction, although we have the algorithms 30 years ago, right? So
Yes.
that's a different challenge. Number of qubits does not have to be less. You have so we had a machine, a Condor, I think 2 years or before. I don't exactly remember. I think 2023 or sometime. That was a 1100 qubits. Do people have use cases where they need 1100 qubits? We didn't find anyone run 200 qubits on that processor or on any processor. People don't have a use case that needs 200 qubits today.
Yes.
So a lot of people keep asking how many qubits, how many qubits, how many logical qubits. What will you do with a logical qubit? Honestly, I'm telling you, people don't know. Right? It's just
Yes.
that people know that okay, something is a logical qubit, something is a physical qubit, and physical we need a large number of physical qubits to map to one single logical qubit. So people keep just challenging these questions. But if you really have a use case, come up with that use case. People don't have that use case. In fact, I'll show you some. I mean, not I cannot show you right now, but in a couple of months, you'll see these papers coming, and they are just 144 qubits, and they are, getting significantly better results than the state of art classical. Right? That these are not utility; they are way far away from utility, and they are potential quantum advantage candidates. They're just 144 qubits. Right? So even with 144 qubits, you can really do so. The number of qubits doesn't matter. Okay, here is
Yes.
a separate story.
That-
Noise still exists, and noise will even exist even in fault tolerant. Okay, so error mitigation strategies will not go away anywhere. We will need error mitigation strategies even after we have a lot of things that we have laid out. Of course, if once fault tolerance comes, and we also are thinking that okay, if fault tolerant hardware is there, we have error correction strategies in place, you might not need error mitigation, right? Error mitigation is a post-processing routine. If I'm being able to correct these errors while the circuit, it's best, right? But
Yes.
I'm not trying to clarify that one question. I'm trying to clarify this concept
Yes.
because different people had different answers, and that is what worried me. That these concepts like superposition is a big power, right? But we should understand what it can do, what it cannot do. So similarly for each of these concepts, when you go to quantum optimization lectures, maybe in a couple of days, I think Anil or someone is going to touch on that. You will actually come up with this tunneling effects, right? That's why I thought that okay, if it has not been taught in the previous module, I will just briefly mention what it is. In fact, tunneling also can potentially help in quantum machine learning. We just don't know how to leverage it. Think of a loss landscape. So your loss curve goes down, and then it might get stuck in some local minima for some time, again goes down, again stuck, again goes down. You guys know how loss functions look like, right? A typical graph where your x-axis is your number of iterations, y-axis is your loss, right? Now your loss is going down, down, down. Now you will hear a lot of these concerns. There has been a lot of work on barren plateaus and things like that. But there was a time when people were very concerned about quantum machine learning and its barren plateaus, right? Because the right kind of choosing the right answers becomes a very big problem, right? So if I am being able to choose a right answer, I have a potential higher chance to not get stuck in a barren plateau. However, I will not know the correct answers for every data set, right? So I might get stuck in this barren plateau. Now, if I can utilize quantum tunneling, think of this. So you are at the first local minima, your loss was coming down, you are stuck at some point, and you tunnel through the next local minima. So basically, think of this as a ball moving along this line. and maybe I should connect my iPad. Um, so okay, yeah, sorry, I should have done this before. I was just trying to explain how this loss function would, I mean, how, if it's a ball moving along the line of this loss function and it is at that local minima, it will suddenly go straight and it is going to fall to the next local minima, right?
Ma'am, your screen is visible.
Sorry?
Screen is not.
Yeah, I know.
You're,
I
you're
have.
not sharing anything, right?
No, I was not sharing anything. I should actually connect my iPad and write this because if I show a graph, then I think that would make more sense. Mm,
Yep. One thing, yep,
yeah.
while you're doing that, can I
Yes.
go ahead?
Yes. Yes. Please.
So, so this this layout of this course is completely confusing, Anupama. What happened was, say for example, module 3, the videos released were same as the videos released in module 4 also, except that you mentioned about introduction to QML. You are going through that slides in one of the first live session. Now they are part of module 4. So which should have been in module 1, moved to module 4, the introduction, and Q3, module 3 and module 4, both of them have the same videos. And it's so haphazard that they were not laid out. You might have given everything to them, but people who have uploaded and put them into the modules did not know what is what, and they just uploaded things without even looking at it.
So I went in and checked last week. So
Yeah,
module one, the namings that was one of your
yeah,
questions
that was fixed.
were
Go to
corrected.
module 3, just module 3.
Yeah.
This is what was released module 3 last week. And if you
Right.
go to module 4, you'll see the same thing.
No, 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 no. Module.
QGAN's lab, ensemble learning, and unsupervised QML algorithms, they were there in module 3 and module
And the
4.
video, okay, okay. So they did not move it out of module three, and they again, okay. So actually, it was a lot of content that was in module three. The point
Exactly.
that module 3 should have just this, module 4 should have this, and
Yeah.
they did put it in module 4, but they forgot to remove it from module 3. And this okay, this is supposed to be the very first video, and this is placed in module 4. Okay, they did
Yeah.
correct all the namings.
Namings are correct, but thing
Okay.
is actually, yeah, and
And
if
what I
you,
did is I also asked them. I think they did it here. Yeah. So for example,
oh, lab
the
notebook, they
lab.
have put it.
Yeah. So what happens is, suppose if you go here and the lab. That I have been doing, because Quantum Lab is no longer accessible, it's sunset. So what I had done is I had given them the links to the exact notebooks that people can follow, and this is a detailed tutorial, not just a notebook. So it has everything, and this is not going to sunset, this is not going to change, so everything it's properly explained, it's all there, right? Every code is there and people can just copy and directly run it. So this is a much better way to understand. So they did not have a way to now upload it, right? And okay, so unfortunately this portal does not allow them to upload IPython notebooks, so I
You
didn't
know,
give them
if you go to reading material,
IPython. So,
sorry to interrupt.
so,
If you go to reading materials, there is an option to give a link to, uh, yeah, notes here. You can give the link to, they can
yeah,
give
so
link to
that also they have put some here. Okay, it is a
something, yeah.
little upset. Okay,
Yeah. If you go
okay.
to course 1, it is all nicely laid out. If you go to course 1 and
So
see the
course
reading
one,
material,
because course one had a TA when we first started. Course one had
exactly.
so the second one also had a TA. I don't know. This year we don't have a TA. I think that's the entire problem
That's
has
a
become.
major, major drawback for
Because
us to.
Kolila
So,
doesn't actually, I mean, poor thing. I don't expect her also to understand quantum and do it all. She's doing everything very diligently. Okay, so at least she changed everything. And what I told her is that VQC, the notebooks have changed. So
yes, yes.
have it here. So she put it as a separate one. So the notebook that I would discuss here in the lab, she has put it here. this one first link, and entangling capacity tutorial is here, and I now see it's also there in the yes, it's also here. Entangling capacity. I think there was a question last live classes about entangling capacity expressibility. So I thank you. Okay, that is here in the reading material. Actually, module 3 should not have all of this. Module 3
Yes,
becomes very heavy if you expect someone to do all of this in one single week, right? So
that's exactly happened to me. I've been spending a lot of time going through them.
So I really wanted to push out GANs, I mean quantum GANs, and unsupervised out of module 3. I'll just tell them that these three things had to be pushed out. They did move it, but I think they copied it. They didn't move.
Yep.
Yeah.
So looking at this one, unfortunately, what happened was these assignments are not getting aligned with the modules. Earlier, means in course one, everything was aligned. So what was taught, there was an assignment.
So
But here, because of this haphazard way of giving things, assignments are not aligned. Not worried about answering the assignments, means of course I have to answer them, but problem is I'm unable to understand whether whatever means if assignments are given, some questions are given, and if there is not in the module, how do I understand whether modules are wrong or assignments are wrong?
Okay,
Assuming
assignments shouldn't be wrong because assignments have been validated and kept it according to the content. So that shouldn't be wrong, even if there is some video that has been copy pasted, or there's some repetition. The assignments are definitely not wrong, but I will still go through each of the assignments again today and try to get back to all of you. Um,
exactly. Thank you
Maybe
so much.
in the
So
in by today afternoon itself. Yeah.
Thank you so much. And
I yeah, I know. I should have found a TA who would actually have done this. In fact, last week I did go through. So my login was not working, but the previous week before the live session. So after the live session, I spoke to them and they had enabled me. I went back. I checked. I told them the titles and they changed everything. They put it. They told me that they cannot put a IPython notebook, so they put this separately as well. So yeah. Sorry, Raghubir has a message. One second, I have to stop presenting. Stop sharing. Yeah. Sorry to intervene while we are losing. Can we have these conversations after 12 p.m., please? Sure. These are questions from the class, so I have no option but to take it. Okay, so the plan for today, again, same things in the live class. We try to answer all of your questions. We can answer all of your questions, or I can go ahead and show the industry use cases as I had promised. If I do that, I will take 30 odd minutes minimum to show you guys the industry use cases. Post that, we can take questions, uh, or if you guys want questions around the modules, that we can cover those as well. Whatever you guys
I
want.
have one question that I want some clarification. It looked like a basic question, but this is what I'm not able to synthesize, means understand. We were talking about in the QML features and data, right? Features follow number of qubit, it means features are qubits, means we pack into qubits, and the circuits are the ones that we use for number of data points, right?
Mhm.
So once I give a circuit, how do you what do you mean by qubits? I mean, I know I may be like sounding like very basic, but when I look at a circuit, what do you mean by the circuit? We all see is the qubits, right? Each qubit is drawn with some gates and all. So what do you mean by the circuit in that one?
Yeah. Okay. So, were you able to go to the platform, create something, create a circuit, create something? Let me
I'll share my screen if you want.
let
Actually,
me
what I'm
share
talking
my screen. Sorry, hold on. Let me share my screen.
Yeah, sure.
I'll try to show you guys what is a circuit. Because if you don't know what is a circuit, I mean, it will be hard for us to. So we did show composer, I think, in one of the live
Yeah,
classes.
composer.
You see the qubits here, right? And let's say I create a circuit like this. Let's say this is my circuit.
Mm-hmm. Yes.
Let's say this is my circuit. Okay.
Mhm.
So when you this is the exact quantum circuit that you have designed, and
Mhm.
you want to run it on, say, some hardware. So it will do some sort of a transpilation and then run it. Now,
Yes.
you will have a final circuit based on whichever hardware you are choosing. So let's say I have chosen a hardware which is, but the results will be the same. So the results will be typically roughly this, right?
Mm-hmm.
Roughly this. And the code will be this.
Mm-hmm.
But the difference will be that when the circuit is transpiled, if the circuit is running, say, on a 120 qubit device, you will finally have not 4 qubits but 120 qubits.
Mm-hmm.
4 out of this 120 qubits chosen. But when it runs, it will show you that, okay, 120 qubits. You have a device, you have a layout, and you have some 4 out of 120 qubits selected. And which are those 4 qubits? You can see those 4 qubits as well. And that's how you will have this circuit created. You'll potentially not have a Hadamard. Let's say you run it on some device which does not have Hadamard. That also, I think we showed last time, but I can still go back and show. So if it does not have a Hadamard, it will have some combination. Yeah. So for example, this one doesn't have a Hadamard. So whenever you create a Hadamard, it will be broken down to a set of, say, RX, RZCX, right? And that's how you will finally have that circuit created, right? So your
Mm-hmm.
exact gates that you have user defined might not remain the same, but that is what was the quantum circuit.
Circuit. Yep.
And if
So in
next we talk
yeah,
about quantum algorithms, you can think as quantum algorithms and quantum circuits are roughly the same.
exactly. So the one that you are describing here, what we say is, okay, there are 4 qubits, and so we can use 4 features. And how many means once I say I have like 10 data points, how do you represent 10 data points in this
Each
circuit?
circuit, each circuit will load one data points, 4 features. So, okay, what are your 4 features? I think this we discussed in the very first class also. So, let's say
Yes.
your 4 features are color of eye, color of hair, type
Mhm.
of hair, and height of the person. Okay.
Yes.
So for first person, all these 4 features are put in these 4 qubits. So the first circuit represents the first data point or the first person.
Mhm.
Similarly, you will have 100 people, so 100 circuits, and then you run all these 100 circuits, right? So in a variation
Okay.
algorithm, you will be running all these 100 circuits for, let's say, 200 iterations.
Exactly. Yeah. Now, yeah, I'm coming to the point. So that is a where. So this is one circuit with 4 qubits, right?
Yes.
Exactly. So there was a question in assignment. They asked 5 data points and each containing 3 features,
Mhm.
and they have given 4 circuits, 4 answers, two of them with 3 qubits and 2 of them with 5 qubits. Okay. So there are a number of 5 data points means how do you differentiate this one? Can I go ahead and share my screen?
Yeah, yeah, sure.
Yep. Now let me share my screen. That's what I'm not understanding actually. Uh, See, this is the question we have. So how to understand this one? So first one and second one, both of them represent uh, 3 qubit states, but there is only one circuit, right?
Sorry, this is question number 3.
No, not this one. Oh, you are sharing it?
No,
It's in
you are
the.
sharing your screen.
Oh, I was sharing. Oh, sorry, I was sharing the wrong one. Sorry. Uh, Let me share the correct one.
This is which assignment? Module 1, Module 2, 3,
This is module 3.
Module 3. Okay.
Module 3. Oh, sorry. Yeah. And this one. Okay. Hmm. Oh, can you see this one?
Yes, I can see. Yes. Which of the below circuits can be used to
One.
get a kernel of 5 data points? Okay. Yeah. Yeah.
Okay. So here, how do you understand this question? That is why I
Question is
said
very simple.
I'm
Question is very
saying
simple.
basic.
Let me help you. Question is very simple, and I think this we discussed in the very first class.
Yes.
So you have three features, and if you are using, say, there could be different types of ways that it is not always that three features will be three qubits. But if you are saying Z feature map, what is Z feature map? It's first order poly Z encoding, right? So when you do first order poly Z encoding, and if you remember in the very first modules classes, I have shown a bunch of encoding schemes. First encoding scheme is Z feature map. Okay,
Yes.
second was
Yeah.
polygs and so on. So you saw how I did the encoding. It was directly I was taking the values. So as many number of qubits, as many number of features, that many number of qubits. So if it's
Mhm.
three features, by using Z feature map, it's either the option 1 or option 2, because those are the only ones where you have three qubits. Others have five, right?
Yes.
The answer could be 1 or 2. Now you
One
say
or two.
which
Yes.
of the, because I mean, because we are talking about three features using Z feature map.
Mhm.
So if you have studied Z feature map, you know that in Z feature map, as many number of features, that many number of qubits. What's
Yep.
the
Exactly.
confusion here?
Okay. Thank you. Thank you. I'll stop sharing. Sorry.
Yeah.
Yeah, it will be one or two, I know, but when it said 5 data points and five, okay, Z feature map.
Number
Okay,
of data points is separate. Number of data points has nothing to do with qubits. So just
qubits, yeah, exactly.
go through the videos once more. You will see in the encoding. So encoding strategies are very, very important, right?
Mhm.
Encoding strategies are the first step towards any algorithm. So it doesn't matter how many QML algorithms we go through. The first step will be encoding classical data into quantum states. And for
Yeah.
that, you will need some quantum encoding algorithm, right? It could be Z feature map, ZZ feature map. I mean, these are the names on Qiskit when you actually. So why I have given you? I want you to generate these circuits. I want you to write them and see it for yourself, feel it. Then you will realize, oh, this is possible and this is not possible. Immediately you get to see, right? You will know
Mhm.
how to do it for 5 data points, right? You can create a CSV of 5 data points. Just put in 5 numbers and see how it works, right? So I really want you guys to touch and feel these things, right? That would definitely help. Any other questions from module 3? We can cover next
Mm,
minutes, and then
I'm
maybe.
good with this. Thank you.
Okay, sure. QC6, please.
Ma'am, like in when we are using this feature as qubit and data as circuit, right? So I really could not understand once how this particular probability density functions we are able to create through circuits, and how we can verify that it is a right circuit for our data, like how to do that, like what are some of the steps, or are there any uh, uh, things that we can do to really map how we decide this circuit works for this data.
Okay, so I'll try to explain this again here. Yeah. So and I'm explaining this with respect to kernel estimations. So the same concept actually happens in probably multiple algorithms in multiple times. For VQC, it was a different thing. For kernels, as you said, right, you have different data points, and I think this is the exact diagram that I would have created in the course. So let's say I have few data points and I create some probability densities around them, right? And I have some other data points also, and I create some probability density functions around them as well. Now I have a new data point incoming, right? And I want to know that, okay, which class it belongs to. So what I will do is I will have a sum of probability density functions here. I'll have a sum of probability density functions here. Then I will try to create, okay, a mapping with this line, a mapping with this line, and I'll see how close this point is to this line or this line. And I'll say, okay, it belongs to this one because it is closer to here or it is closer to that, right? That's a simple concept that we know of, right? And this is exactly what we are doing in kernel theory also. Now, the question here that QC6 is asking is, I am running these quantum circuits. How do I know whether the quantum circuit I have run is correct? And how do I know that the quantum circuit is generating a kernel matrix or not? So let's try to understand what we do. And I'll take this example of the same question that is there in the assignment. So I have 5 data points and I have 3 features. Let's say my features are x0, x1, and x2. Okay, and thereby I will have, let's say, 5 data points for training because I'm doing a kernel SVM. And let's say I have, just to have a different number, 2 data points for testing. And in kernel SVM, I would have told you that, okay, so now how will you create the circuits? Let's first try to create some circuits. So let's say it's 3 features, and let's assume that we are using Z feature map. So I will have 3 qubits, right? Now this is Q0, Q1, and Q2. And I will create some circuit. Let's say I first put everything into uniform superposition, and then I have, say, some entanglement. Let's say I have full entanglement, and then I do some measurement. Let's say this is my circuit. I'm making some very toy circuits, don't go by them, but let's assume this is all that we have. Okay, and let's assume this is a good circuit for now. We'll come QC6, we'll try to help you that, okay, how can we know that whether this is a good circuit or not? This is a very, very good question. So just hold on with me. So now I have this circuit. This circuit I have to have 5 times. So this is my, say, C1 to C5, right? I desire to create a kernel matrix. And we have discussed this in class that each entry of the kernel matrix is basically an inner product of 2 data points, right? So basically I have, let's say my data points, I have named them, let me call this F1, F2, F0, F1, F2, so that I can call my data points X's. So I'll call this as X0, X1, X2, X3, X4. Okay. So each is an inner product of 2 data points, means inner product of X0, X1. So this is X0, X1, then this is X0, X2, X0, X3, this is X0, 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 X, hold on. Cleanly, right? Yeah. So this is X0, X0, then this is X0, X1 till X0, X4, right? And same we go till here. This is X0, X4. This is XS, this is the 0th one, and this is the 4th one. Right? So here we say this is a 5. This is a 5 cross 5 kernel, right? Now this is my, why should I write it here? This is my training kernel, which is a 5 cross 5 size. I will have to create a similar kernel again. Again, it will be inner product, but now I will do inner product between the training data points and the test data points. So let's say my test data points were Z0, Z1, right? So now I will have a 5 cross 2 wherein I have x0 to x4, and here I have z0 and z1, right? So this is x0, z0, x0, z1, x4, z0, x4, z1, right? So so basically I'm trying to say that, okay, I have these two kernel matrices. This is what I finally need to design, right? Or somehow I need to calculate each of these values, right? For each of these values, I will now run some quantum circuits. So let's say now, how many quantum circuits will I have to run for each of them? So for my training kernel, right, I have to run how many circuits? 25 circuits, right? So training time, 25 circuits. Test time, 10 circuits. What is each circuit encoding here again? The circuit still stays the same, but the circuit will have, for say, one data point, two data points. So it is trying to encode the inner product. So you're calculating inner product. So every time you're running these circuits, you're calculating this inner product, the value of just x0, x0, inner product of x0, x0. That's all you're calculating. And then you're putting it here. You're putting it here. You go on and fill this kernel matrix. This is all you need to do in quantum, right? Because you are assuming that this kernel, let's say, is a kernel that you cannot construct using classical computing. That's why you're doing it using quantum computing, and you create this kernel, right? Now you say that, okay, once I have these kernels, I will use some classical optimizer post that anyways. So I'll use some classical optimizer, and then I will try to find out, okay, whichever was the closest, and I will try to find a diagonal and say that, okay, these are the points that are closest to my decision boundary. These are the points that are not optimized. And that's how I find my best line, like, or similar kind of a max margin concept, right? And then as along with that, once I have this test kernel, I will say that, okay, based on these 10 circuits, I will say that, okay, these data points z0 and z1 should have this kind of labels because they were closest to, say, x0 or x4, whatever, right? So that's how you got the class labels for z0 and z1, right? Now in like this is the entire process that you are doing in a kernel SVM. You did all of this assuming this is your ansatz, or this is your quantum circuit that enables you to create this kernel which is better than classical, right? This was the assumption that you started with. Now, can you create better kernels? Can you create a better ansatz? For variational algorithms, we studied this concept, or studied some measuring units called expressibility and tangling capacity. It's not that they are not holding true in this case. However, what in this case, because finding inner products is the main thing, whichever circuit can get you the best way of inner products. The inner products you can calculate mathematically, right? So you calculate it mathematically, and then you create a quantum circuit, and you say that, okay, this quantum circuit's output should be this, right? So whichever quantum circuit, or you generate a bunch of quantum circuits, like basically these are generate a bunch of ansatz, and whichever quantum circuits are closest to your mathematically calculated inner product, you can just say, oh, this is my best kernel to this is my best quantum circuit to go with, right? So here in this case of kernel SVM, it is easier. Okay. Now this will not lead you to quantum advantage. Forget that story. Don't get into that. But I'm just trying to answer QC6's concern, which was, how do I know that this quantum circuit that I'm choosing is good or not? So in this case, it is very easy. A quantum circuit that can correctly compute my inner products is the best circuit. Okay. However, had this been a variational quantum algorithm like a VQC or a QGAN or several other algorithms, now choosing the ansatz, or even for quantum Boltzmann machine going forward that you would see and so on, choosing the correct ansatz is becoming a bigger problem now. if you have a correct, I mean, if you the better the answers you have, the closer to real results you will be. How do you now know that which is the best answers? There have been several things that people have been doing in literature. One way is, can I compute these metrics? For example, can I see if better entangling capacity, because this is a concept that quantum has and classical doesn't have. So if I have more entangling capacity in my quantum circuit, does that lead to better results? People have done that study. People have studied that, okay, if I have more expressibility, does that lead to better results? Okay. And several other kind of metrics. So one is a metric driven. So for each answer, I will try to quantify how much is that metric, and then do a correlation between that metric and the accuracy, and say that, okay, this metric is a good identifier or a good way to qualify my answers for my problem. Okay. Now, the other side of the things that people have been doing is, can I use something like reinforcement learning, where I will construct this answers. Okay, so this is not covered in the class most likely, but there are some papers. So I will just briefly mention, because there's a question in QC6's mind. So now let's say I have the same qubits, same feature encoding is fine. But then what I do is, I am taking some action. So you can now, if you get, if so in reinforcement learning, what we basically do is, we say that, okay, there is an environment and we will take some actions, and at each action we are going to measure the outcome, and we are going to see that whether this action was a good action leading to some good result or leading to some bad result. If it's leading to some good result, I will give that action some reward. If it is leading to some bad result, I will penalize that action and not do it again, right? So now let's say my first step was initializing them to equal superposition, right? So I will first apply a Hadamard. I applied a Hadamard and I calculated my loss function, and I saw that, okay, my loss function, nothing really changed. So it does not help or does not matter. I said, okay, let me try another Hadamard. Okay, now I say that, okay, it is, it's not, it does not deserve a penalty. However, not a significant reward, or the very small reward, continue. So I continue, I went with another Hadamard. Now I gave a C naught here, and it gave me a penalty, right? So and then I have to say, okay, I want to remove this. I have to remove this C naught because it gave me a penalty, and I will actually apply here a C naught. Again, try to validate whether this gives me a penalty or a reward. Okay, let's say I got a reward. I said, okay, this is good. I will keep this. I'll keep this kind of C naught, and let me apply another C naught like this, right? So at each stage, what people do in this kind of reinforcement learning based answer selection, this is the sort of work. You can Google up and read more about it. So this is one way to create better answers, that instead of manually created answers, and you would have seen in that paper, Sukin Sim's paper, where they had manually created some 19 circuits for which they compare computing entangling capacity and expressibility, right? So one way, and people have been actually doing that in variational algorithms, is they have been creating manually these circuits. And I would say this is more of their back of hand calculation and experience, right? So I know that this kind of circuit will work better than that kind of circuit. Some sort of an experience we already have with running so many circuits, so we will think that, okay, maybe this answers is better, so I will go with this answers. How many repetitions of such answers, I really don't know. So maybe let me do this experiment with different number of repetitions for different setups, and then whichever gives me best result, I will choose that as my best result. But in all of these cases, my my quantum circuit is hard coded, right? I went with the assumption that I know that this quantum circuit is good. This area of work is an alternate thought to it. I don't know what is the right quantum circuit, so I will not start with any such assumption. At every point, I will create a gate and I will construct this circuit and I will continue to measure. Now, the measurement could be different things. You can measure, say, the same metrics. You can say that, okay, at every, so you add a gate and you say that, okay, how much is the expressibility now? If expressibility is increasing, I will give a reward. If expressibility is decreasing, I will give a penalty. Right? Or you can say, I'll do for same for entangling capacity. Or you say, I will do it for the actual loss function of the problem. Right? So whatever you want to define as your metric, that is separate. Basically, the RL algorithm is going to consider this metric and say that if this metric, and you have to define the what is the reward. You give a reward of +5, let's say, and a penalty of -1 for something, right? You have to define all this, and then you continue to train. And at the end of this iterations, you will finally get some answers. This answers you go ahead and use. So answer selection is a very, very challenging thing in the field of variational algorithms. And if you see, a lot of people have actually gone ahead and stopped using. So we have completely stopped using variational algorithms. For example, for chemistry, because now we have a much better algorithm like sampling based quantum diagonalization, we don't use VQEs at all. Right. But yes, at that point when these algorithms had not been identified or invented, there were no other algorithms to run in the near term area. So yes, variational quantum algorithms were used. But we know that, okay, variational quantum algorithms have these concerns. For example, you have to run it for so many iterations, right? Running for so many iterations is challenging, right? In real quantum devices. Then what is that ansatz, right? That's a complete estimation here that you are doing. That's a challenge. So yes. And you post the research paper that I mentioned now. I don't think it's one such research paper. I think there are multiple works in this area. You can just Google up reinforcement learning based ansatz selection. There was a time when a lot of people were working, including, in fact, me too. So there are a lot of people who have been working on this. Some people might have some research papers. I'm not exactly sure about one paper, but yeah, I can find them. Okay, Madam, can I power for clustering using QM? Yes, so that is actually in module 4, you will go through clustering algorithms. So there are certain clustering algorithms. For example, Karanidis' group had proposed a quantum k-means. There are a bunch of algorithms that have been proposed. Some are fault tolerant, and I would the way to answer to think about this would rather be what do I want to do in clustering? Why is this not doable classically? And what in quantum can I utilize to have a say to make quantum clustering algorithm, which is going to give me an advantage over classical, right? What in quantum can I leverage to build that algorithm? So that can be done. Yes, it can be done. So QC6, was this clear? This is a very important
Yes.
point, answered selection, but was it clear?
Yes, ma'am, this is clear.
Very good. Yeah, QC57.
No, one basic question. So when you apply the measurement in different qubits, right, your outcomes change, right? So how do I infer which one is right for me? Because if you apply measurement this first qubit, it's going to collapse to a state, like let's say 0000 and 0011. And then if I apply my second measurement in second qubit, I get different outcomes. But what do you infer from this?
So, this is actually again a very good question. So, if I apply measurement on, so some of these things we know because you can mathematically compute it, right?
Correct.
Versus, I'll tell you where it becomes challenging. So let's say I have some measurements that I apply here, and I apply measurement in, say, Z basis. Okay, I can actually compute at each stage what is the state here. So this was 0. So this is an equal superposition of 0 0, and then this is what is the state here, what is the state here, what is the state here. I can exactly measure and find it. Right? However, and because of practice, some people will say that, okay, I know, you ask me for certain types of problem, I will just directly say I want to measure it in X basis, I want to measure it in Z basis, depending on the problem. We Somehow we know what is going to be right, or mathematically you can compute it till this stage anyways, right? These are not black boxes. The challenge becomes when I want to run this in, say, in a large ansatz, right? And for example, I want to do mid-circuit measurements also. I want to save my qubits. I want to do qubit usage, reuse. I want to do mid-circuit measurements. For a larger circuit, now it becomes difficult that, uh, and should I do it for Z basis throughout? If I do it for, and sometimes the problems are like this, that people typically will run multiple setups and then try to evaluate which setup gave things better, right? One way, a simple mathematical way is, I think, more reliable, and that's why I follow, and a lot of people follow this. So if I can calculate the state here, I know what kind of state I want to achieve. I can calculate that state. So that's what we'll go. In some cases, you want to see that, okay, I want to construct an identity here, right? So you know exactly what to do to create that identity. You can do that. Uh, there are some cases where it is not very obvious what to do, and those cases, people typically run a bunch of experiments and then choose the results.
Okay. No, my question was, yeah, I got like we get an outcome, but how do I use it for my decision making in a real time?
Yeah, so no, okay. So when you have to compute this, you exactly know what you are trying to compute. You are trying to compute an inner product, right? So the output of this circuit should be a value which you have to put here, right? Now when you have put these values, finally what you do, you are just trying to find out, okay, most of these will be zeros, which of these are ones, you know that those are your support vectors, and then you have this test kernel, which of them, I mean, which data point is closest to which zero or one, you just label it accordingly, right? You have the sign. So
Okay.
at that stage it is not difficult. At that stage it is very obvious. What I thought that you are worried is, how do I apply these measurements, and these measurements, should I apply them in Z basis, X basis, or Y basis, right? Because if you apply measurement in a different basis, of course the results will dramatically change. So that is it is a known problem, but it does not have one prescriptive solution. But finally your calculation remains the same.
Okay.
Calculation is a simple classical optimization, the same thing that you do for, say, classical SVM. So you can actually here use a classical SVM as the classical optimizer. You can use anything as your classical optimizer. Your classical optimizer, what does it do? It finds out that, okay, which of the points are closest to which points. So now, in order to find the closest points, you don't want to do a mapping from, say, for all. So here what we did a 5x2, right? Now you will say that, okay, when here your training data was 5, ma'am, so you could do it for 5. Now if your training data is very large, how will you do it? Valid point. So now in classical SVM, what we do, even if my training data is 3 billion, I will find out the support vectors, and the support vectors are going to be very sparse, because most of this matrix is zero, right? It is zeros. So this is a very sparse matrix. So now when I have a very sparse matrix, I just have few ones here and there, right? So those ones is the exact support vectors. I know that, okay, those are the data points that exactly matter, and the other data points don't really matter. So I will just run for, say, let's say my number of support vectors was 10, right? I mean, in this case it has to be less than 5. How can I write 10? Let's say 2, right? So then I just have to compute with these 2 into the test data points, which is 2. So just a 2x2 would have been sufficient, right? And again, this 2, 5, these numbers are very low numbers, and then don't indicate anything. However, if you think of this as 100 into 100 circuits, right? So you had to, let's say, run, you had 100 data points in training. So for a QSBM, you would have to run 100,000 circuits for training. Now you know how long these circuits would have to run. So typically what you will do is, the way to calculate this is 4,000 shots per second. Okay, so let's say you have 100 circuits, and okay, let me just break this 100 circuits to say 70 train and 30 test. So basically I'm saying total 100 data points, okay, and 70 for training and 30 for test. So basically you will say 70 into 70 for training and 70 into 30 for test. Okay, so now how many shots can you run? Let's say you are an open access person, so you just have 10 minutes of free time. So how many shots can you run? So let's say 70 cross 70 into how much should it be? It's a 250, right? So if I do 70 into 70, this is 4900. So 4900 circuits, and if I, let's say, 250 shots, so 250 shots will take how much time? 1 second is 4000, so 250, 4000 into by 250, 4000 by 250 is 16. No, no, no. 1 second. So I can do 4000. So 4000. No, actually, I should have done the reverse. No. So 4000 shots in 1 second. So 250 shots would be how much? 1 by 4000 into.
Yeah.
I just did the reverse. So it should be 250 divided by 4000, which is 0.0625, right? So this many seconds for 250 shots. I'm just assuming 250 shots you will be able to run, right? So then so 0.0625 seconds into 4900, right? So this is 306.25 seconds. So divided by 65 minutes. Okay, fine. Yeah, so you can do it in 5.10 minutes. So your training will complete in 5.10 minutes. Again, similarly, you have to calculate that this is okay, 2100. So if you can do say 250 shots, 250 shots is 0 0.6. Let me do it. 0. Say no, 0. 0.0625 into 2100, which is 131 seconds. So 131.25 seconds. I should write this. So again, this divided by 60, if I do, it's 2.1 minutes. So 2.18 minutes, right? So you can actually run this under, not under, I mean 7 point some minute, right? So under 8 minutes, you can complete a QSVM run on a data set of size 100 using 250 shots, right? So I mean, okay, reason why I showed you all this calculation is I want you guys to run it on any data set, right? I don't think that is going to be a part of your assignment or things like that, but just to get your hands dirty, just to learn it for yourself, pick up any data set from Kaggle or whatever you'd want to do. Iris data set, it's a very small data set, 4 features, or any data set of your choice. You can just feel free. And I have done this calculation for 100 circuits, sorry, 100 data points, but you will have your own number of data points. I will not suggest you to go to say some million trillion data points, but on a smaller subset, just try to understand how you can do. Just do the calculation so that you know that okay, I am still under my free 10 minutes. Everybody has 10 minutes of free access. Okay, and it's a rolling window, so you have, if you say finish your 5 minutes today, right, and then the next testing you do next week, so after 28 days from today you will get back your 5.10 minutes, and then after that, whatever time you finish this, you will get back this 2.1. It's a rolling window of 28 days, I think, or 30 days, something, 28 days maybe, and you get but you have 10 minutes. So you have 10 minutes per month, which is also a significant amount of time to run a large number of experiments, I'm telling you. And students have been able to do, like, people have been able to do experiments in the realm of 144 qubits, right? So they have done, so they did 120, up to 120 qubits, and they were actually doing it under 10 minutes. Then 144 qubits also they did, but the results, I mean, the results are actually pretty good, and they have applied for research credits, and we are trying to give them research credits because sort of quantum advantage work that is coming up from the Indian ecosystem that I have been telling you guys. So then people get research credits and have access for to machines for a very large time, but yeah, and for free. But even the first 10 free minutes can also run something very valuable, and that's exactly what I'm showing you here, right?
Thanks. One last question. This 100 circuits you mentioned, right? So the other one is considered as one single circuit. Is it the ansatz that you have built?
Yeah. So ansatz could be the same. So for all the 100 circuits, the ansatz, let's say it's the same, right? It's the same way that you are loading the data. So it's the same number of qubits. For all the 100 circuits, let's say you have 3 qubit, right? So 100 circuits means 100 data points. Each circuit, you are loading for one data point. You have such 100 circuits that you have constructed. 70 such were for train, 30 such were for test.
A circuit is basically meaning a data point, is it?
Yes. The number of, okay, this is something that is coming. So I just discussed this a couple of minutes ago. Guys, you're not listening to me. So number of data points is how you map in you create your number of circuits. And number of features is mapped into your number of qubits for most types of encoding schemes. For example, in the very first module, you'll see I go through a lot of encoding schemes, right? When I start variational quantum algorithm, I think the very first video is only, it does not cover 4 steps of VQC. It just covers the first step of VQC, which is the encoding strategies, right? And I go through a lot of encoding strategy where you see Z or ZZ or say angle encoding. In all of these cases, as many number of features, that many number of qubits, right? There are other encodings, for example, amplitude encoding and so on, where you can actually decrease the number of qubits. It need not be as many number of features. But here we have been considering going with this assumption that it is, see, I had written it here, right? It is a Z feature map. So if it is a Z feature map here, so it means as many number of qubits, as many number of features, right? So going with that, your circuit remains the same. Circuit is this, number of qubits, number of features, how many circuits, as many data points, which is 100. How do you construct a quantum kernel? This is how you construct a quantum kernel. How many such circuits you will have to run, as many data points, that is how the kernel size would be. So the kernel size for training will be 70 cross 70. The kernel size for testing will be 70 cross 30. So each entry in this kernel matrix is an inner product of 2 data points. How will you get that? You will get that by running a circuit. So how many total circuits? As many total here circuits, as many total here circuits. So, and then you will have to do the time estimation. So this is just a time estimation of how much time it actually takes to run on a quantum computer, right? Typically what we have observed is 4,000 shots. Any circuit, doesn't matter, the number of qubits don't matter, right? But 4,000 shots typically takes 1 second. So that's why I calculated, if you have to run these many number of circuits, how can you do it in under 10 minutes? So that's why I just went with 250 shots. You will be able to run your training in 5.10 minutes and testing in 2.18 minutes.
Clear. Thanks.
Very good. Okay, so any other?
Madam, I have one doubt.
Please.
Can we compare this timing with the classical computing? Maybe for the same problem. Suppose the training you have written maybe 5.1 minute, and the testing is 2.18 minutes, right? So
Yes.
if we compare with classical, how much better it will be?
Classical, way faster. So if I do a classical SVM, I will not require 1 second. I think it will be under 1 second for my training and for my training. under 1 second. So you can just immediately do this, say use classical SVM, just use scikit-learn, and with scikit-learn creates a similar data set. First do it on scikit-learn on classical SVM, and scikit-learn will directly have a function called SVM and just pass the training data and the test data, and then do a print of time. Okay, you'll see it would be, I think it would be less than a second, or maybe 0.00 some seconds. And then you can run the same things on a QSVM, right? In the same notebook, you can have both. I think I'd show a similar thing on one of the problems in my videos also. I don't exactly remember, but I think I show. And you will see, okay, comparison of a classical SVM and a quantum SVM. Of course, a classical SVM running on a classical hardware will be way faster. And this is actually not just quantum time, right? This 5.10 minutes is quantum time plus classical time. So imagine this. This is you are this is the circuit running time. No, I'm sorry. This is the circuit running time, which includes some latency, some classical time, some resource allocation time, all of that. However, you will also have some classical SVMs or some optimization on top of it, which will not take more than a second. So if the total here is 7.28 minutes, I think it would still be under 7.38 seconds, maybe, right? So sorry, 38 minutes. So hardly a 1 second would be your classical optimization time, which is in addition to this total time. And this time is your running of your quantum circuit plus some waiting time, some latency, all of that, right? So you are running a quantum device on cloud, so you have your internet latency. All of that factored in, we say that typically all of that factored in 4,000 shots, 1 second. So yeah. And see, in classical and quantum, another thing that you will say is classical is deterministic, right? You are not running it for multiple shots. Here, you are running it for multiple shots. So you're actually not just doing this experiment seven. So you're running this 4,900 circuits, not once. You're running 4,900 circuits 250 times, right? So I'm saying 250 shots is basically that many number of times you are running it so that you get 250 results, because you assume that out of the 250 results there would be, let's say if I run this on simulator, I would say okay, 250 times it will be correct results, but if I run it on hardware, I'll say 200 times I should see the same bit string, which is my correct results, and 50 times I might see some other small random bit strings, right, which are incorrect results, right? But 200 times I should see. So that's the reason you are running this for multiple number of shots. So if you see, you are doing a way more computation here. 4,900 circuits run 250 times plus 2,100 circuits run 250 times. That's the total number of circuits that you are running just to get this one result. So if you compare it at that level, of course, classical is way more easier, better, faster, and all of that. That's not the reason why we want quantum. Right? The reason we want quantum is assuming that there is this kernel in quantum SVM. That kernel you cannot construct in classical. Right? If you are constructing a kernel which is a linear kernel or a Gaussian kernel, you can do that very well in any of the classical computing. Right? So then you don't have any advantage. Forget advantage. This is more expensive a hardware. Why will you run so much and do all of that? But if you think that, okay, in classical, I cannot really construct this type of a kernel or a very higher order kernel, which let's say I can construct. For example, let's say D-log kernel, I cannot construct classically. And now I have some way that I can construct a discrete logarithm kernel in quantum, which is enabling me to learn this problem in one shot, right? So all the, like I showed you, right, all the blue data points get mapped to say ket 0, all the red data points got mapped to ket x, right, or ket some, so ket 1, right, let's say. And then you say that, okay, it is, I can draw any plane in between and they will always distinguish between the two classes, right? So I don't need to do the classical optimization step at all. I can immediately find that. So that would have been something very powerful, and that would lead to very good results on data sets that we are not able to solve today using classical. So those are the cases where we will use these quantum algorithms. It is not fair to probably compare it, and maybe not actually not fair. It is not valuable to do the same kernels on classical and quantum, right?
Yes, thank you, madam.
This time estimation thing that we went through today is something that I can bet you that, I mean, you guys are some 40 people here, right? So these 48 people, they know it, and you can go ahead and check with even very good academicians or people who have been running these. They don't know how to do this time estimation, right? um, and this is something that is very important for us to learn or understand to be able to do these experiments.
Yeah, thank you, madam.
Ma'am, a small question, ma'am. Like, so when we compare the classical ML algorithms with this quantum kernel based or whatever the algorithms that are coming in, and I mean, is there any standard procedure for when we, what are certain type of problems, like if at all there is no proper uh, convergence of the algorithm in classical, can we try for quantum? Is there anything like that, or is there any benchmarking for quantum to give the advantage or anything like that, ma'am?
Yeah, it's a very common question. So, okay, I'll try to answer it from quantum machine learning perspective, but also from quantum computing perspective first. Is there a question is there a prescription where to use classical and where to use quantum? Okay, so unfortunately there is no such prescription, but you can think of this because people typically say NP hard problems. NP hard problems is not the right answer. The reason, we don't have a proof that quantum will actually solve NP hard problems, right? So that's why it is not a right answer. Now there are problems which are, so I mean, one analogy that people give is, what are the kind of problems for which you will use a CPU versus a GPU, where you need, like, where it is taking it is becoming infeasible. So let's say you want to do you want to do something on top of an ECG. So you need real time results. So your results needs to come in, say, in the order of seconds, and the results is coming in the order of hours. So then you know that, okay, I am running it. If I'm running it on CPU, it is not it is not correct. I need to run it on GPU, or I need to do more algorithmic improvements, or run better things. But I need to. So that is something that we say that this is infeasible, right? So it should run in seconds. It's running in hours or something. So that is incorrect, right? So that's like the basic understanding. Now, where to use quantum and where to use classical? Quantum in those places where you see that, okay, is this problem can leverage some quantum principles which will lead it to be able to answer things better. For example, let's say you are doing Hamiltonian simulation. You know that people have been doing Hamiltonian simulation using classical, but with certain assumptions, because I can never model all of the properties exhibited by this molecule together, because this equation is a very large equation, right? Let's say a time dependent equation, or let's say a time independent, like a Schrodinger equation. So you cannot model this classically enough. That's why you are using quantum algorithms to do that, right? With assumption, without assumption, but that is one baseline, that, okay, these are places where I will use quantum. Now, for, let's say, for optimization, I have a traveling salesman problem, and traveling salesman problem, people have been trying to solve them using classical algorithms for ages, right? And now let's say I have like 12 places, so I can actually, up to that, or up to some number, I can do some classical estimation and solve it classically. But as soon as I start inserting like even one extra thing, now these computations become very large, and then I there are potential ways that we can solve them in quantum versus we cannot solve them together in classical, right? So if your underlying algorithm can leverage something in quantum for which it can be better, those are cases. Now, coming to quantum machine learning, if we are trying to do it on, and remember in my first live class also I mentioned this, if you remember that four quadrant slide. If you try to do it on classical data, uh, probably there is uh, no advantage in the near term. Why I am saying this? On classical data, these classical ML algorithms, they have like been there last 40 years. They can potentially take care of these problems better. Now, you will not have advantage in, say, a quantum advantage in sending emails, doing video conferencing, and so on, right? We know these are easy problems for classical. There are certain hard, for example, discerning patterns. So I cannot. So maybe there are a lot of these very complex patterns in financial modeling, which are very hard to discern by classical ML, right? Rule based models and so on. You will see in banks, it's not all classical ML. Also, it's the bunch of rules and heuristics along with some classical ML algorithm that are used, right? So there are a bunch of things that are exist there, and they even after that maybe it is not reasonably solved. And there could be ways that, okay, using some quantum computing algorithm you can maybe solve it better. So it is not only about being faster, it could be faster or better, but in both cases it should be verifiable, right? So those are cases where we would say, um, we want to use I mean, we can potentially use a quantum algorithm than a classical algorithm. I am not getting into application domains. I think that was the slides that I had to show you guys today. But if this helps you understand that, okay, for which kind of problem will I use a quantum computing algorithm or a classical computing algorithm? Also, if you think about algorithmic development, right? So if you see that, okay, today you have these kind of algorithms that have been developed, but there is a scope. Of course, algorithm development, there is a lot of scope, right? What is the areas where we should potentially develop algorithms? In all three, I would say simulation, optimization, and machine learning. But in machine learning, the problems are different. The problems are that, okay, how can I load more data in a better way, right? Today data loading itself is a big problem. Like you guys, we have been talking about this, right? 100 data points is 100 circuits, right? 100 circuits is like, oh, this is like a lot. And then let's say I have 100 features, so that's like 100 qubits. I want to be able to do dense mapping in the number of qubits. I also want to be able to do dense mapping in the number of circuits. So if so there are simpler ways that people have been doing it, right? I would say these are not the most effective. But let's say your data points do not vary significantly. You will say that, okay, I will not use some sparsity theory things that people have been doing in classical machine learning, also the same things people have been doing here in quantum machine learning, and saying that, okay, I will not run 100 circuits because out of these 100 data points, or say let's these 70 training data points, let's say there is a lot of overlap between them, or there is say they'll put some threshold and say that, this features don't differ by say 0.003 or something, and then that will be considered as one circuit. So I will not run on the other circuits which are sort of very close to these circuits. And that's how I pruned it down, and I made it from 70 data points to, let's say, 30 data points, right? There were 40 others which were closer to these, so they were similar data points. I will not train it across because I know that my model will going to learn. So these are things that people are doing today just because quantum machine learning algorithms are not being able to run to that scale, right? So that's why I mean, if I want to really run on say billions or terabytes of data, I I cannot just compute, okay, differences in data, and then I say that, okay, I will not run it for terabyte of data. I will still run it on a smaller subset of data. So it is basically an inability. I mean, our inability to run for terabytes of data today, right? So we need to be able to create better algorithms in that space. Okay, so there are two questions. I think QC29 first.
Good afternoon, ma'am. My question is regarding facial map, madam.
Yes.
So, I want to deal with for simplicity, I'm asking you by using iris data set in that four features will be there, madam.
Mm-hmm.
So I have used encoding for those four features into quantum state using ZZ fusion map with two qubit entanglement. But now you have told that for three features you have mapped with direct one to one qubits. So one to when I have to go for this type of feature map and when I have to go for this one to one mapping.
Sorry, could you be a bit louder? So you are doing it for iris dataset,
Yes,
ZZ
yes.
feature map. So it's one-to-one mapping. So in iris dataset, it's four features. So you will have four qubits, and yes, one-to-one mapping. So I did not get the question.
Yes, ma'am. Actually, I did with encoding with two qubit entanglement madam, by using ZZ feature map.
Uh-huh.
Uh, in that one, uh, so the two qubit entanglement is linear way I have used. So
Right.
feature dimensions are four, and so when to use one to one, when to use uh, this type of encoding four features into two qubit or three qubit entanglement, only two qubit entanglement. Is there any formula like in digital logic design for
Okay,
any?
I think I got your question. So your question is when to use what type of encoding?
Yes, yes, yes,
Yes.
ma'am.
Okay,
Yeah.
okay, yeah, yeah, very good. Yeah, very good question. So uh, Z feature map, let's say poly first order poly Z encoding.
Okay.
What does it do? It does some rotation to the qubits. It does not have an entanglement, right? So by
Okay.
means of rotating, why are you rotating a qubit? You are saying that okay, my so let's say my okay, let me try to draw and if help this. So this is my q sphere or block sphere. This is my qubit here, and I'm saying that I will just rotate my qubit till here, right? In a Z feature map, I will just do rotation. So now it spans through, say, some Rx and some rotation, some R theta. So now I have a state space which is this surface. So if I mean I know I'm very bad at drawing, but let's say this is not a circle; it is a sphere. So all the data points in this part of the sphere is what your qubit um, can very well look at, let's say. Okay, so your qubit has access to all the data points in this surface of this sphere, right? So if your training data, test data are part of this surface, it will be able to measure it very nicely. Now let's say you have another sphere and you have two qubits, and you say you entangle them, right? You not only have a rotation but you also do some rotation and some entanglement. In effect, you have now spanned this entire cube, right? This entire state space. Let's say this, if this looks better. So now so these two qubits are now able to look at the entire radius or the entire surface of this sphere. They are able to look at. So even if your data points were here or here, this guy would have missed it. This guy will not miss it. So if the data point is here, 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 it can see everything in any place, right? So that is the, I mean, that's the reason why people say that okay, ZZ is better than Z, because in feature map, Z feature map is just first order poly, right? So you are basically applying some poly operator on the first order. So you're applying some, say, rotations across, so I, X, Y, or Z. So but just one. But here you have the ZZ feature map is nothing but a second order poly. So second order poly means you have two things that you are doing. You are doing I, X, Y, Z, but then you are doing something else. So you can have some entanglement also here, and then you are applying these entanglements and you are applying some rotation. So now you are, because you are doing multiple operations, you can potentially, I mean, I'm not saying always you will have that entire sphere, but you can do some tweaks and find, and say let's say you wanted to look at this particular half of the sphere, right? So one half of the sphere is populated, the other half is not populated. I mean, those are things that you can do. So this becomes a reason why, say, ZZ feature map is generally better than Z feature map. Now, but the problems that, okay, ZZ feature map or Z feature map, both of them are costly in terms as costly in the number of qubits, right? So there are other feature maps as well. You can say that I have angle encoding and I have higher order angle encoding, which are also similar. They have uh, more qubit consumptions, but they have probably better encoding feature. So yes, higher order encodings, higher order angle encodings, or Z feature maps. These could be typical choices for people to I mean, go with the feature map. There is again similar. There is no one way that, okay, this would definitely be the best for you, but I mean, the assumption here is maybe entanglement will help, right? So if this guy doesn't have any entanglement and this guy doesn't have just has one angle rotation, maybe this and this guys are better than say a first order poly or an angle encoding. Right? So there could be something that is slightly better, but not for every problem. You cannot directly say that. Now, you might say that, okay, I'm talking about all of these guys. Why am I not talking about amplitude encoding, which is the only one that we have studied so far, which has some um, uh, compression in the number of qubits. Now, although it has compression in the number of qubits, this definitely will not give you a advantage over classical, because when we try to do this, we have been packing more information, although, but we are to be able to unfold this circuit is a deeper circuit, so this does not lead us to and this is classically doable also, so this does not give us some advantage as in comparison to, say, these guys, right, which have entanglement and other things. Now, there is one thing that I think I have mentioned, and I think I saw it in the reading materials, yes. So there is something called quantum random access coding. I think I would have discussed it in some class, maybe in the encoding one or somewhere, and I have put in that paper also. So basically there are other encoding schemes which are trying to say that, okay, I will ensure or inculcate entanglement and other good features. Along with that, I will try to do qubit compression, right? So QRAC, there are different things in QRAC. So for example, there is something called a 3-1 QRAC, right? Wherein basically you're trying to have three bits compressed to one qubit, right? So you can also have 2-1 QRAC. So 2-1 QRAC is actually better. The probabilities of getting it back is higher. I think these probabilities would be somewhere around 0.85, and for this, I think the probabilities will fall. The probabilities will drop. And I think they had a paper where they said that 4-1 QRAC is not possible, because at 4-1 QRAC, when they were packing four classical bits into one single qubit, I think the probability at that time was dropping below 50, right? 0.5. So below 0.5 is like meaningless, right? So that's why they said that 4-1 QRAC is not possible. But of course, things have been changing. So maybe now we can go back, revisit, and create some better encoding algorithms there, where you can have more compression. So there is two parts to this. One is that, okay, you are trying to get more compression done in terms of number of qubits by means of the encoding algorithm, while not decreasing the probabilities of being able to recover it, right? So it still has to be some good encoding scheme which has these properties of quantum entanglement of other things, but it should also reduce the number of qubit usage. So that's typically how you can consider these encoding algorithms. But yes, no one single prescription. Is that clear, 29?
Okay, madam. Okay, madam. Okay, madam.
Yeah, thanks.
Thank you.
Shayan?
Hi, ma'am. In context to which where quantum possibly gives an advantage, so can we intuitively say that wherever classically we have certain kind of assumptions, and we are not getting a good result out of the classical circuit, we can probably try for a quantum circuit, because quantum machines are themselves probabilistic in nature, and therefore they can model that assumption better. Like, is this a good way to think about it?
Yeah, it is correct. It is roughly correct. Yes, roughly correct. And that's what we are trying to say. It's just that for some cases, okay, I'll tell you the only places where people debate this is, I have very large amount of data. I have a very large, let's say I have a LLM, and even if the LLM is not performing very accurately today, it was going to get better over time. So yeah, those problems we don't want to participate. Versus those problems that say okay, in chemistry, those are problems we know that quantum will help, right? Problems in nature which we cannot, as you said, right, we are trying to go with some assumptions and still we are not able to solve it well. So that part is very correct, right? So let's say in chemistry we are going with some assumption. We do homolumo, like higher order orbitals you will remove, lower order orbitals you will remove. Why? You will say that okay, the molecules, the closest, so let's say the center is my so here is my proton guy, right here. So my mass, my nuclear mass, and then I have some orbitals, right? So you'll say that okay, the electrons residing in this orbitals are very much grounded, and because they are very close to the protons, they have the attraction is also high, so they don't jump around this, so they will stay here. So because they are not going to change, let me not consider that. So that's called LUMO, right? And then you say that this higher order guy, I mean, this guy is anyways doesn't matter, for my interactions, and I'll not I mean, I'll forget them, right? So because you are unable to do it for all electrons, I'm just making some bad diagrams of electrons, okay? But yeah, let's say this is a molecule and these are the total number of electrons. Don't ask me what molecule is, I have no idea. But let's say I say that okay, I am going to consider these electrons, these are the ones which are active and which are actually mattering to me. The other electrons I will not consider. This is what chemists have been doing all along, because classical chemistry cannot, I mean, there are no good simulation algorithms which can actually do it for across all electrons. So you might have heard of DMRG, I mean, like classical state of art, some classical state of art algorithms. They also, I mean, go with certain assumptions, and then we are trying to model the molecule, right? However, in these cases we have quantum algorithms, for example things like sampling based quantum diagonalization, wherein you will see that okay, these are quite close to DMRG results. And I'll just give you guys, because I think this is something that you should do in your quantum chemistry or simulation. I don't know whether it will be covered or not. I'll just give you an example, and I'll tell you why people are moving away from variational also. So so the assumption here is, if let's say if you have fault tolerance, right? Just assume that you have a fault tolerant hardware. There was a molecule, there was this paper where people were working on Fe4S4. Fe4S4, I think I mentioned this in the last class. It takes it is called the cradle of life and all of that, right? So
Yeah.
this particular molecule, it requires somewhere around 77 qubits in this SQD algorithm. Now let's say you have fault tolerant computer, then you would need somewhere around 4.5 million fault tolerant qubits, and that is going to run for say around 13 days, and that is going to complete this experiment correctly, right? But I am assuming fault tolerance exists. I have 4.5 million qubits, then it will run in 13 days. Now, let's say you are going to study VQE. I know Chaitanya will cover VQE, I think. So when you will go through VQE, it's a variational algorithm very similar to what we have done in VQC. It's just tries to compute your eigenstates and eigen vectors. Here, you will need much smaller number of qubits. I don't exactly remember the number of qubits, but here this is going to run somewhere around 300 years. Why I say that this is going to run 300 years is because this is a variational algorithm. It is iterative. It is going to take, um, several iterations in order to completely converge to the actual ground states. It is going to take a lot of time. Now here you might run it with the same number of qubits, and I'm assuming that each circuit is taking some 10 microseconds per circuit, let's say. And with that, I would say somewhere around 300 years. So I will run this experiment. I will not live to see the results. Now, in this quantum centric supercomputing that we have been able to do, and this is an old result that I'm talking about, sampling based quantum diagonalization. Again, the same assumption, 10 microseconds per circuit. Now, this is running in 12 minutes of quantum hardware time. Okay, and around 1 point, not exactly 1.5 hours, also less than that of a supercomputer time. So this is the classical time. Okay, so total is around 2, actually not 2 hours, less than 2 hours. Less than 2 hours you are doing subspace estimation. Again, then I'm going with the same 10 microseconds. So this I can easily do this experiment. So this is the reason why we are going with quantum centric supercomputing, and these are the cases, these are kind of use cases which we are saying that you will see a quantum advantage immediately. We don't speak of that, and we are not able to speak of that in quantum machine learning because we don't have such algorithms. In fact, there is a recent line of work where people are actually creating Hamiltonian based that for encoding strategies, because the current encoding strategies are very costly. They are actually trying to think about, okay, can I actually do this Hamiltonian or subspace sampling kind of things for my data loading? So my first step, which is these encoding strategies, which are costly, instead of that, can I use something like an SQD? And once I have that, post that, I have my same quantum. So there is a recent paper, I think in January, it came up from Konal and team, that actually shows something like that for quantum machine learning. So that could be one way of mitigating one of the problems that we have in QML today, right? But this is the reason why we say that, okay, these kind of things will are potential advantage candidates versus quantum machine. And this is the reason why quantum simulation is a potential advantage candidate than QML.
Got it, ma'am. And which quantum property does SQD leverage in order to get this advantage?
Superposition, entanglement, all of that. The main thing, SQD is nothing that but SQD is trying to sample a lot of bit strings and create this large matrix. So you will see that, okay, there are these, say, these bit strings here, and then you will say that, okay, once I have created this large matrix, I have to do diagonalization, right? Now this diagonalization I will do classically. So this I am doing classically. So this experiment, if you see, this is actually in this is a supercomputer. This is Fugaku. So this we did with IBM and Riken together. So this was a Heron processor. I don't remember which processors. They tried with multiple processors, but all Heron. So this is some Heron processor, and this is some Fugaku. There is an updated paper actually, which is even faster, and the results are closer to DMRG results. So what it actually shows is, okay, if DMRG is here, earlier your SQD was here. So this was SQD, say 2024. Yeah, okay, no, actually I should not write like this. Let's say, so if you look at the results, this is Hartree Fock. Okay, this is the going by this assumptions, this is the kind of state, the lowest eigenstate basically you're trying to get, and the lowest eigenstate that you can get by, say, DMRG is here. So definitely Hartree Fock is very bad. And what we had shown previously when SQD was first discovered, SQD in 2024 was here. Now SQD has come down here, right? I'm just making up lines. They're definitely not lines. They're all curves. But yeah, and just to show you guys, right? At different levels of number of qubits and different experiments. But the results, what I'm trying to show is that the gap between the classical approximation algorithm and the quantum algorithm, still, it's not that the classical approximation algorithm is also not the best, but the quantum algorithm, till it gets the See, so time is not the most important. If you ask a chemist, they'll say that okay, if the quantum algorithm is as good as the classical algorithm or better, only then it is meaningful to me. Otherwise, why will I use that, right? So this gap has to be decreased. Doesn't matter how long SQD is taking or how long DMRG is taking, right? We do this time comparison with respect to say fault tolerance or pre-fault tolerance. This is pre-fault tolerant, right? VQE. You can run it today, right? This is pre-fault tolerant. You can run it today, right? But if it is still not given you that quantum advantage, the quantum advantage will be the day this SQD is below DMRG, right? Or at least equal to DMRG, even if it takes more time. So DMRG takes 8 hours. DMRG takes 8 hours, right? So today we are saying that okay, SQD is taking 2 hours, DMRG is taking 8 hours, but we are still, I mean, at least the IBM papers will not still claim quantum advantage, because even if it is doing things faster, you know that the results are not as good as DMRG, right? Until and unless it is as good as DMRG or better than DMRG, you cannot claim quantum advantage. But yes, I mean, things have been progressing. So at least this gap from here to here, it has been reduced. So we are very hopeful that this can be reduced further. But that's like the state of art, or these are the quantum advantage stories that are there today.
Yeah, thank you, ma'am.
Any last question? Okay, QC29. Okay, I think QC29 had asked the question earlier. Okay, any other questions for today?
Yeah, there is a new concept called ZX calculus. That is
Yes, yes. ZX.
I tested the question card. So should we rely on ZX calculus or traditional mathematics framework when working with quantum machine learning or in quantum computing in general?
Yes. So ZX. Okay, so ZX calculus is another mm, mm, method. It's not very recent, you know. I mean, if you look at Bob Koike has been talking about this for a couple of years now. It's just, I think more rigorous experiments or more rigorous things will come. This work started around quantum NLP. I think finding these structures, yes, and some people in crypto are also very interested in using. I think there is more work to do there. Um, but yes, I mean, so mathematically correct. Mathematically, they are being able to show that okay, we can do some learning there. We need to just um, construct circuits out of it. So how do I finally run these things? So that engineering part aspect is not there today. So I know I know a ZX calculus. I know that okay, how to a quantum a quantum state can be described in this format. How do I create quantum circuits that are described in terms of say a ZX equation? And then how do I create these algorithms? So there are some algorithms that people have been creating, say for example, um, uh, natural language understanding, right? So doing sentence similarity, right? So they had some work where they were creating these sentences in the form of ZX calculus, right? The bearing, the directionality, and so on, mapping that. So if the sentence is that I ate an apple, I have the noun, the verb, the dependencies in the sentence, and I use that dependency from that sentence and I map it to ZX calculus or rules of ZX, and I can create a corresponding not circuit but a line, right, or a dependency graph. Now, from that dependency graph, because quantum circuits are also dependency graphs, right? So can there should be a way that I can create these circuits. Now, we need to build algorithms on top of it. It's a very nascent area, I would say. But once, if we can build some algorithms on top of it and show that, okay, this is a better way to do quantum machine learning, that would be excellent. Yeah. There's not a lot of work. Bob's team has been doing a lot of work in this area. If you want to really study that, DiscoPy is what they have as their um, repo. Uh, but there's not a lot of groups focusing on this yet.
Okay, and Ruby on Rails is used or Python is used? I saw somewhere that we have started using Ruby on Rails for effective.
So DiscoPy, they are using that, but so DiscoPy has a Python version of that as well.
No, no, no. In IBM also, I think in Qiskit side, I think we started using you. I mean, the IBM has implemented something on Ruby on Rails, not on the
On on on
Python side.
on what?
Ruby on Rails,
Ruby
ROR.
Ruby on Rails అన్నప్పుడు. Ruby on
Okay,
Rails.
Ruby. No, so IBM, so Qiskit has been moved to Rust. So a lot of
Sorry, just
functions
not
they have
Ruby on
been
Rails.
moving to Rust.
Uh-huh.
The advantage there, and this has been happening like last 2 years actually. So if you look at Qiskit 1.0 release, we wanted to make Qiskit lean and clean and all of that, but also more performant. And naturally, Rust was a better choice. But at that time, I think around 19-20% of the functions were moved to Rust. Versus now, if you see, significantly things have been moved to Rust, which has increased speed. So if it is much faster and performant and stable, then what it helps you is you can run these functions for way longer. And so I told you, right, there's a lot of hardware optimization that is being done, but there's a lot of software optimization that has also been done to be able to run these deeper circuits. So one of the software optimizations that I meant was, moving a lot of functions on Qiskit. So there's something called PyO3. PyO3 is a wrapper where, so as a user, let's say I can still continue to run or write a code on Rust, but write a code on Python. But then the classes that I'm using, these classes can be easily converted to Rust, or the Qiskit classes that I'm using are actually Rust classes. So now and that layer is being done by PyO3, and then it runs way faster, right? It does not have memory leaks, it does not have a lot of problems that Python has. That's the reason why Rust was chosen. And there's a significant improvement. For example, I'll tell you, I was doing this kind of conversions for so an SQD is very very optimized, so there is not much of improvement, but there is a slightly different algorithm which we called sampling based Krylov diagonalization, SKQD. Now in on SKQD, on the same sets of qubits, like I did experiments on, I think up to 22 or some qubits for some molecules that I was playing around with. And for them, if you do the Python profiling versus you convert just two functions, so Hamiltonian generation and circuit generation, these two functions were taking the largest amount of time. So I just wanted these two functions to be converted to Rust, and then again I did a profiling and benchmarking. So there is a 3.5 to 5.5x improvement based on the number of qubits, of course, but let's say a 5 times improvement in SKQD, right? If you convert things from Python to Rust. And as and when you start doing much bigger experiments, a 5 time improvement can be huge, right? Can be like, say today whatever is 12 minutes, maybe that can come down to even further. I mean, 12 minutes, I know it is already Rust converted, but yes, I mean, think of some other algorithm which is taking significantly longer. If 5 times speed up is a significant thing. So yes,
Okay.
Rust conversion.
So as a new developer for quantum, so what we should do? Do we start with?
Python is enough. No, Python is enough. It's that inside of Qiskit. So you say, yeah, if you know Rust, nothing like that. I mean, you can actually become a Qiskit developer, and that's something that. So when we were wanting to last year, we have wanted to hire a lot of people in Qiskit in India. At that time, we were actually looking for people who have like Rust background or who have quantum background and can also code. We got a lot of people who are PhD quantum but cannot code. people who are good software developers but don't know quantum. So that's a problem that it's not just in India, it's a problem throughout. But yes, I mean, if you know Rust, nothing like that. I mean, please let us know. I mean, the team will be very, very happy to get people like you. But if even if you know Python, it's enough. So if you just want to learn quantum or do quantum, Python is enough. Things that are ported to Rust or changed to Rust, you don't have to write in Rust. You are still writing on Python. So, in fact, Qiskit has not only been I mean, the base functions significantly have been rewritten to Rust, but also we have a C API now. Okay, because if you look at this quantum centric supercomputing, we are trying to work with a lot of these HPC people, right? And HPC people typically use C, right? And there are certain advantages, disadvantages, again, C versus Python, that is a different debate. But so now in Qiskit 2.2 we have a C API that enables us to actually run, say the HPC people can run C codes, and Qiskit will still take care. So Qiskit will take care of it's a C code, Python code, Rust code, everything. So Qiskit is strong enough to take care. You can be still a Python developer or a Python programmer who is doing quantum experiments using Python. So if you want to be a quantum expert, you don't have to know all the different languages, right, per se. You just need to know the quantum concepts, and if you can code it up in any language, Python is the easiest. That's why it was built on Python, so that more people can access it and easily run it. So yeah, that's also perfectly fine.
Okay.
Okay, maybe we are.
And one thing, last session I provided one BB8 for implementation. Have you got time to check that?
No, I didn't. I haven't been able to. But yeah, BB84 is a protocol that I know the protocol. But if you really need more help, maybe I can connect you with people who are experts in that area.
I implemented that, so I just want to check whether my implementation is correct or something improvements can be done in the implementation.
So there are implementations available. If you want to check across them, you can also check. Or if you want to do something more novel on top of that, I think I can connect you with people. So just drop me an email, and that.
Your email in chat. I will just do it.
Yes, sure. I will just write my email ID here. I can connect you with people who are working in that space as well.
Okay, thank you.
Okay. Thanks, everyone. See you guys next week.
Thank you, ma'am.
Thank you.
Bye.
Thank you, ma'am.
Thank you.
Thank you.